Okay, so let's start here. We're talking about um, solutions here. But the first thing we got to do before we talk about solutions is talk about the water molecule. Okay, so water molecule is very, it's special. And without it and without its properties, life wouldn't be able to exist on this planet. What makes it special is mostly because it is this polar molecule. So polar means that one part of it has a partial negative charge and the other part has a partial positive charge. Okay, so it's kind of like a magnet. You know how a magnet has a north and a south end? Well, a water molecule has a positive end and a negative end. All right. And the negative end is located near the oxygen atom, and the positive end is near the hydrogen atoms. Okay, now water molecule is actually a bent molecule. It's bent because oxygen actually has two lone pair electrons. It has electrons on this side of it. So those electrons push the hydrogens closer towards one another. And so it looks like kind of like Mickey Mouse ears, if you think about it, some little ears on it, right? And the reason that the oxygen has a negative charge while hydrogen has positive charges is because of their electronegativity. So if you remember, we talked about electronegativity a long time ago. Or not a long time ago, but not. We talked about like periodic trends, and electronegativity is the tendency for an atom to pull electron density towards itself when it's in a covalently bonded molecule. So in this case, we have a covalently bonded molecule. We have these hydrogens covalently bonded with this oxygen. And the oxygen, being that it is more electronegative than the hydrogens, pulls electron density towards itself. Okay, so it pulls electron density towards itself. So it becomes a partial negative. So this little sign here, that means partial. It's not a full-on negative, it's a partial negative. And here, this is a partial positive. Okay, so if you ever see that little symbol, this means partial. Okay, now, because of that, uh, water forms hydrogen bonds with itself. So hydrogen bonds are actually these things called intermolecular forces. So intermolecular forces, we don't talk about them in depth in this class. We're not going to talk about all the different types of intermolecular forces. Just this one we're going to talk about. And intermolecular forces, inter means between, like international. Like international means between nations, okay, or international. Get it? The bonds that we've been talking about before, like covalent, ionic, metallic, those are intramolecular forces. Intra means within. Intra means within, so within the molecule. Okay. So hydrogen bonds again are intermolecular forces. They're slightly weaker. They're slightly weaker than the intramolecular bonds. So they're slightly weaker than covalent bonds and ionic bonds. But hydrogen bonds are still relatively strong. Okay, they're still pretty strong. They're the strongest intermolecular forces there are. Okay, and this intermolecular forces, hydrogen bonding, is a result of the positively charged hydrogen being attracted to the negatively charged oxygen of separate water molecules. So you have one water molecule here, another water here. The hydrogen of one water molecule is attracted to the oxygen of the other water molecule. It makes sense, right? Opposites attract. You have a positive hydrogen and negative oxygen, so they're attracted to one another. Okay. Now, because of this strong attraction, we get several properties of water that are kind of unique to water here. First one is that hydrogen bonding results in high surface tension. So if you ever see like water bead up, right? Makes beads when it gets on surfaces. If you ever fill up a water glass, or you put anything like water on anything, it'll just kind of like form this like bubble on top of it. And also like bugs can like walk on water basically. And these are all due to the high surface tension. Okay. Now surface tension is the definition of surface tension is the tendency of a molecule to be drawn inward towards itself, or basically like the attraction. The water molecules are attracted to one another, so they all form like they're all attracted to one another. They pull in on one another, right? They draw inward on one another. Okay. Next, there's something that can interfere with those hydrogen bonds. So we can kind of disrupt those hydrogen bonds and eliminate that high surface tension and some of those other properties, the beating up of water. The molecules that interrupt that, we call those things surfactants. Okay, so the surfactants interfere with hydrogen bonding in water. Okay, so surfactants often lower the surface tension, and if you put, so an example of a surfactant is soap. So soap. If you put soap in water, it kind of ruins that whole idea of water holding onto itself. Okay, now water will hold on to the surfactants and cause some disruption there. Okay, it could ruin the surface tension of the water. Okay, this is important too. Like if you think about it, if you put surfactants like soap into water in like a stream, right? You're going to lower the surface tension. Now the bugs are all going to not be able to be on the surface of the water anymore, and they may fall in and drown. And usually fish like to eat the bugs off the surface, right? But if they're coming in, falling into the water, they're going to die, and then there's not going to be any more bugs there. But I don't know. There's lots of things that can happen with lowering the surface tension. Okay. Now, soap, we often refer to it as like an adapter molecule because normally oil and water don't normally mix. Okay, we'll talk about why they don't mix later on. But basically, actually, we'll talk about that actually maybe tomorrow. But basically, usually like dissolves like is the general idea. So polar molecules dissolve polar molecules, and nonpolar dissolves nonpolar. So the more two molecules are alike, the more likely they are to dissolve one another. And oil and water are very, very different. Oil is nonpolar and it's a big molecule. Water is polar and it's a small molecule. So they do not normally mix. However, soap acts like an adapter. It has a hydrophobic end and a hydrophilic end. Okay, hydrophobic means water fearing. So the hydrophobic end attaches itself to oil. Okay, it's a non-polar end. It attaches itself to oil. The hydrophilic, which is the water-loving end, attaches itself to water. So one end attaches to water, and the other attaches to the oil. So you can kind of see it in this picture here. Right, this soap molecule is this long zigzaggy thing. So one side is attracted, one side is attached to the water, the other side is attached to oil. Okay, and that allows the oil and water to mix. And that allows the oil and water to mix. Okay, so again, we kind of call it an adapter molecule. Just like if you have if your computer doesn't have an HDMI outlet, but it has a VGA, you can get an adapter to hook your computer up using an adapter that takes the HDMI and turns it into a VGA, something like that. I'm sure you've all experienced something like that before, right? Maybe charge your phone or something like that. Adapter molecule. Okay, that's soap. Okay, another property of water is that it has a relatively low vapor pressure. Okay, so because those hydrogen bonds holding the water molecules together, it has a low vapor pressure. So we talked a little bit about what vapor pressure was. We talked about gas loss, but basically vapor pressure is the pressure above a liquid created by the evaporation of that liquid. Okay, so the more it evaporates, the more vapor pressure there is. Okay, now because water has a relatively low vapor pressure, there's not going to be a lot of pressure above the water. Okay, it also means that water will have a relatively high boiling point. Okay, because boiling point is when vapor pressure equals atmospheric pressure. Okay, if vapor pressure is low, then it's going to take quite a bit. Then the vapor pressure. Then the boiling point will be the temperature has to be relatively high. Okay, to increase the vapor pressure enough to make it equal to atmospheric pressure. Okay, so when you heat something up, that increases the vapor pressure. Okay, and vapor pressure has to equal atmospheric pressure when something boils. Okay, so if it has a low vapor pressure to start with, right? Low vapor pressure to start with, we have to heat it up to make it higher and higher, the vapor pressure higher and higher to make it boil. So water has a relatively low vapor pressure, so we need to heat water up significantly to get it to boil. Okay. Next property of water. One of the most unique properties of water is that that water is actually less dense as a solid. It's weird to think about, but most things, pretty much everything, is going to be more dense as a solid, because if you think about it, as something cools down, the particles are going to get closer and closer together, and eventually they're going to stop moving and they're going to become more dense than they would be in liquid form. Liquids and solids tend to have actually relatively very, very similar densities. Okay, but usually the solid is more dense than liquid. However, water is the opposite. Okay, water is the opposite. Okay, water is a really, really strange one. It's one of there's not too many liquids that are more dense than their solids. Okay, now water is actually most dense at 4 degrees Celsius. So at 4 degrees Celsius, water would be the most dense. After 4 degrees Celsius, the water molecules start to actually kind of align. Okay, so normally water molecules are kind of moving, flowing past one another. They're forming temporary hydrogen bonds, right, between the oxygen and hydrogen. They're kind of moving past one another. When they get to 4 degrees Celsius, they're not moving as fast. Okay, and they're the most dense. But as you get colder than that, then what happens is those hydrogen bonds, the oxygens and the hydrogens, start to align into this honeycomb-like structure. And as they align into this honeycomb structure, they actually expand. They're actually expanding. Okay, the amount of space between the molecules of water is actually increasing compared to that in water. Okay. So as it freezes, it gets less and less dense, and then ice is actually less dense than water. Okay, and that's why ice floats. Okay, if ice was more dense than water, it wouldn't float, right? The densest things go to the bottom. So this allows life to really exist here. Okay, when you freeze a pond, right? What happens is the top freezes, but the bottom stays a liquid. Okay, the bottom cold water will stay a liquid, and then fish and other organisms are allowed, they can survive while the top is frozen. It really allows life to exist. Kind of crazy thought here. Okay, next. So those are the properties of water. Now we're going to talk about what can we do with water. Well, with water, we create solutions. As we all know, we can create solutions. We put stuff in water, right? That's really what we want to do, put stuff in water. Okay. Now a solution is a homogeneous mixture. So means homo means the same. So it's the same throughout. So it looks the same throughout. So you can't distinguish the different parts. You can't distinguish the different parts of the mixture. Okay, it's a homogeneous mixture, a mixture where you can't distinguish the two parts or three parts. Okay, it's a homogeneous mixture of two or more substances in a single phase. Okay, this means you can have a solution of liquid, but you can also have a solution in solid state and gaseous state. In solid state, you would have something like an alloy, and then in gaseous state, you get something like air. Air is actually a solution. You can't see the different parts. It all looks the same. Homogeneous mixture. A solution is made of two parts, okay, or more, two or more parts. The solvent is the component that has the highest concentration. Okay, so you can have a solution with, usually there's only one solvent. That's the one with the highest concentration. And then the solute is the component with the lower concentration. So whatever, if there can be more than one solute, there can be multiple solutes. Okay, so this is just an example using like Kool-Aid. So the solvent is the water. The solute is the Kool-Aid mixture. Okay, and even if you wanted to say Kool-Aid and sugar are solutes, because you add a lot of people add sugar to their Kool-Aid, right? And in Kool-Aid, there's actually the mix. There's a lot of different things too. So the solute is just all of these things in there, right? And then the solvent is water. Okay, there can be solutions of liquid and liquid too. And we'll talk about that a little bit later, but it doesn't really matter. This is the most important part. Solvent, solute, solution. Okay. Okay, now there's, we can have a saturated solution, and this is what you're going to do today in the polar activity. You're going to look at saturated versus unsaturated solutions. Okay. Saturated is a solution that contains the maximum amount of solute that will dissolve under a given set of pressure and temperature. So pressure and temperature do affect how much can dissolve in something. So you have higher temperatures, you can usually dissolve more, lower temperatures less. Higher pressures more, lower pressures less. And when we have a saturated solution, that means there's actually going to probably be some solid undissolved particles there. So those particles are actually in a dynamic equilibrium with the ones that are actually dissolved in solution. So some will come out of solution while others will go in, but it's always going to be the same amount coming out and going in. Okay. An unsaturated solution is a solution that contains less than the maximum amount of solute. Pretty simple. Okay. You can add more to it. That's all. That's basically what they're saying. Okay. Now, supersaturated solution is really interesting. What you do is you take a saturated solution, so something that has the maximum amount of solute in it at a higher, so you take basically a hot solution and then you cool it, a hot saturated solution, and then you cool it. Now, as you cool it, that should actually lower the amount of solute that you can dissolve, but the solute won't come out of solution right away. Okay, it'll stay in solution. So we call that supersaturated because it actually has more solute in there than normally could be at that temperature. But because it was already in the solution, it stays in solution. Okay, so it's in solution at a high temperature, and then as the temperature cools, it stays in solution, even though normally it wouldn't stay in solution, it wouldn't dissolve. Okay. Now this is a very unstable state. It doesn't last for long. Little things can, like just agitating it, just like shaking it or touching it or moving it, can cause the solvent, the solute to come out of solution. Okay, it's a very, very unstable unstable state. Okay, and maybe I'll show you an example of that tomorrow. Okay, and that's all I wanted to talk about today. Okay, so if you do have any questions, feel free to ask.